Hi folks, in this video we'll learn about a pretty simple idea called the analysis of variance. And the idea of the analysis of variance, which we often abbreviate ANOVA, A-N-O-V-A, is to try to attribute credit to individual variables in some kind of statistical model. And as you'll see, an analysis of variance is really just a simple bookkeeping exercise. So here's how we conduct an ANOVA. We build up a model one step at a time. So if you're thinking concretely about some of the models that we've seen, let's take the example of the model for predicting reaction time in video games. There we had four sets of variables. There were the variables associated with, well, really the one variable associated with the clutter effect. There was the variable associated with the far away effect. There was the interaction between those two variables. That's three. And then finally, there was the set of subject level dummy variables to get at the fact that some people were faster on average than others. So to do an analysis of variance, what we do is build up that final model with those four sets of effects, three main effects and one interaction, in stages. So you build the model one step at a time, adding one new variable or one new interaction among variables at each step. And at every step, you're asking yourself two questions. First of all, how many parameters did you have to add to the model to account for the effects of that variable? So in the case of a simple binary variable, like a categorical variable with two classes, like far away or not, there's only one parameter that you had to add, one dummy variable associated with that categorical variable. In the case of the subject variable, there were 12 subjects, and in order to account for that, we needed to add 11 dummy variables. So that's just kind of the bookkeeping exercise here. How many parameters did you add? And we usually call that, for technical reasons that aren't worth going into, the degrees of freedom associated with that parameter. All right, so that's the question. How many parameters we add? Question two is, how much did adding that variable improve the predictive power of the model? And you can imagine measuring that in a couple of different ways. The way that sort of historically, classically, this has been measured is in terms of the variance decomposition. And you'll remember this from the discussion of R squared. If you take multiple different models for the same y variable, it's always going to be the case that total variation, TV, equals predictable plus unpredictable variation. TV equals PV plus UV. The question is, when we add a variable, how much residual variation or unpredictable variation did we account for that wasn't previously accounted for? So, you're adding a variable to a model, and you imagine it's sort of like a two-column bookkeeping exercise where some of the variation goes out of this column over here and into this column over here. Extra information in the new predictor that you're adding means more predictable and less unpredictable variation. Okay, so TV always stays the same when you add a new variable to the model, but you take some variation out of this column and you move it over here. TV always equals PV plus UV. Okay, and so what that means, if you kind of go back to the formula for R squared, every time you add a new variable to a model, R squared always goes up, and in an analysis of variance, an ANOVA, we keep track of how much R squared goes up. Okay, the precise numerical value of that change. Another way that you could measure this improvement in predictive performance is using the residual standard deviation. And you recall that's calculated with this formula right here. There's an important difference with R squared here in that this number right here, the residual standard deviation, actually could, in principle, get worse, i.e. go up when you add a variable to the model. And that's because there's both a numerator and a denominator here. This part this sort of sum of squared errors will always go down whenever you add a new variable to a model. But this term right here, because you're adding parameters, this term, n minus p, could actually go up. So it is possible, although it's pretty rare, it is possible for this number to go up. In other words, it looks like your predictive performance, your residual standard error, gets larger when you add a variable to a model. Okay, so those are two ways that we could keep track as we do this bookkeeping exercise of an analysis of variance. And the final result is called an ANOVA table. And that table shows the answers to those two questions. How many parameters did we add? And how did the predictive performance of the model change as you add each new parameter? Okay, so let's take the video game data, all right? And let's just consider this in stages. So what was our first step, right? And let's just keep in mind, total variation for this data, that's the total sum of squared deviations from the sample mean measured in milliseconds. It's this super high number, 39,190,224, and that's not very interpretable. It's just think of that as the total amount of sum of squares or total amount of variation that's on the table to be predicted here. So let's add one variable at a time and track how that number right there gets partitioned among predictable and unpredictable components. So step one, you add the effect due to visual clutter. So that's just one dummy variable. So one extra degree of freedom. And here's your predictable variation, and here's your unpredictable. So we would say the clutter effect gets credit for predicting that many units out of the total sum of squares, out of that many possible. Okay, and that adds one parameter to the model. Simple enough. Okay, now you add the distance effect to the model. That's step two. So now you still have the clutter effect. You're building this model up in stages, like in layers. So now we've got time modeled by clutter and distance, main effects only. And here's the new variance decomposition. You can see predictable goes up from 3.6 million to about 4.8, 4.9 million, and unpredictable goes down by an equivalent amount. And so the distance effect, what's that difference here between that amount of predictable variation and that amount of predictable variation? Well, you would say that's kind of how much credit the distance variable gets in terms of units of total variation, in terms of total sum of squares. All right, step three, we add the interaction of distance and clutter, and we'll return to that table we just skipped over here in a second. You add the distance clutter interaction. You've got these two main effects still in the model, and now this new variable, or this new interaction right here. And now here's PV and here's UV, and PV went up by 183,000 units of total variation. We're almost done here. Step four, we add the 11 subject level dummy variables. So we've got clutter and distance main effects, a clutter distance interaction, and now a subject level main effect that involves adding 11 new variables, 11 new parameters rather, to the model. And here's the new variance decomposition. And so you can see if you're comparing that PV to that PV, it got bumped up by a pretty big amount, 5 million units out of 39 million. All right, so this whole exercise, like add a variable, how many parameters do we have to take into account to get the effect of that variable, and how much does it improve the predictive performance, is summarized in a table like this. And this is an analysis of variance table right here. And so you can see what's the variable added. We start with an intercept only. How many parameters do that involve? Well, an intercept only, that's just like the sample mean. And so our R squared by definition is 0. And our standard deviation, that's like the original standard deviation of the y variables, is 142.9. All right, and now as we add clutter and then distance and then the interaction and then the subject level dummy variables, here's the change, here's the R squared for those models. So it goes up from about like 9% to 12.5% to 12.9% to 22.3%. Here's the delta R squared, like how much R squared is changing, going up at each stage. Here's the residual standard deviation, how much it's going down at each stage. So remember, improved predictive performance means higher R squared in general and lower residual standard deviation. And then here's delta SE, how much that residual standard deviation is improving by or going down by. And you remember, keep in mind that in an analysis of variance table, if you're looking at a row here, we're adding clutter and distance, that model whose R squared you're calculating and whose residual standard deviation you're calculating includes not just this variable right here, but this variable in addition to all of the variables above it. So this model corresponds to the clutter main effect, the distance main effect, and the clutter distance interaction. And so how would you reason using an ANOVA table here? Well, probably the simplest way to reason is like what variable is getting you, predictively speaking, the biggest bang for your buck, right? So here, when we add the clutter main effect, what do we get? We get an improvement of about, 6 units, 7 units in terms of residual standard deviation. Adding distance gets us an improvement of about another, say, 2 or 3. Adding the interaction has a very small effect, only about a 0.3 unit improvement in our residual standard deviation. And adding the subject gets us like an 8 unit improvement in the residual standard deviation. So you can see that this is a way to think about attributing credit to the individual variables in the model, to kind of decompose the variation, analyze it, break it into its parts, and say which variable is accounting for the lion's share or kind of most of the predictive performance of the model. And that's really all there is to an analysis of variance table. I personally like either tracking the change in R squared, or maybe even more interpretable to me is the change in the residual standard deviation, because that has the units of the original quantity. And if you want to connect it to the scale of the original data set, milliseconds of reaction time, that has that same units right there. Okay. And so, in the final analysis here, it looks like subject level effects contribute the most to the predictive performance. The clutter effect contributes the next most. Then the distance effect is kind of in third place. And then the clutter distance interaction contributes the least. Now, an important question here is what actually counts as a big number in this column right here, like a big improvement in residual standard deviation, or equivalently a big improvement in R squared. You can get a sense that some of these numbers are kind of small in absolute terms, like a 0.5% improvement in R squared, or a 0.3 unit improvement relative to 143 original units of residual standard deviation. And again, right now we're just reasoning intuitively about that. What looks big to you, knowing what you know about the problem. As we go forward and as we learn about quantification of uncertainty and techniques for hypothesis testing, we'll be able to put some more teeth to that. In other words, give us some kind of statistically motivated standard for what counts as a significant or a statistically large contribution to the residual standard deviation. For now, it's just sort of using your eyeballs. What looks big, what looks small, and that can give you some rough notion of which variables are buying you a lot of predictive power and which variables aren't.